Hello and welcome to a worked example of how to calibrate a gravity model using an Excel spreadsheet. In order to calibrate a gravity model, we need four inputs. The first is a series of trip productions and trip attractions for each zone in the study area. You will note that the sum of the productions across all zones equals the sum of the attractions across all zones. This is a necessary starting point for the gravity model calibration process. The second input is an observed average trip length. This is the trip length that we are trying to achieve in our estimated matrix. The third input is a skim matrix, which we obtain by skimming the network and recording the minimal travel time or travel cost from each origin zone to each destination zone. The final input is a deterrence function. In this case, I've adopted a simple negative exponential distribution function. And I've had an initial guess of the value of the alpha parameter of negative 0.2. This is the value that I will adjust in subsequent iterations so that my observed average trip length of 11.5 is reproduced in my estimated matrix. In the initial step of the gravity model calibration process, we apply the deterrence function to each cell in the skim matrix. You can see here that the corresponding skim matrix value is input into the deterrence function that I've specified in the top right of the screen. The same function is applied to each cell to come up with an initial estimate of the trip matrix. Now clearly this is a pretty poor estimate of the trip matrix because the row totals are a long way from the target trip productions for each zone. Similarly, the column totals are a long way from the target trip attractions for each zone. However, given the results of this 0th iteration, it's possible to calculate a series of correction factors that we apply to the column values, while at the same time setting the row balancing factors equal to unity. When we do that, we produce another iteration of the calibration process. And you can see that in iteration number 1, we basically take the results from the previous iteration, multiply it by the corresponding row balancing factor and the corresponding column balancing factor. We then recalculate the sum across each row and each column and compare those to our zonal trip productions and trip attractions. You can see in this case that the column totals exactly match our trip attractions. However, our row totals, although closer to our trip productions than the previous iteration, are still out by a factor of up to 40%. These then become our new row balancing factors for the next iteration. In the next iteration of the calibration process, it's just a matter of taking the resulting matrix from the previous iteration and multiplying it by the row and column balancing factors from the previous iteration. So from here on in, it's the same process repeated, but each time you'll note that the row and column balancing factors, these values in red and green, tend towards unity as the model converges. In the next iteration, the matrix continues to change and the row and column totals continue to converge to the target production and target attraction values for the corresponding zones. you note here in this case that the row and column balancing factors are now only out by plus or minus 24%. In my final iteration, iteration number 4, you can see that the row sums exactly equal the production values and the column sums are fairly close to the attraction values for the corresponding zones, the error being plus or minus 12 or 13%. The total number of trips in the matrix is 1000, which is the correct value. Now, I could have done more iterations at this stage to try and reduce the errors associated with the row and column balancing factors, but for the sake of brevity, I've stopped it at this point. Now we can calculate the estimated average trip length. This is done by multiplying the number of trips in each cell in our estimated matrix by the corresponding generalized cost value in the skim matrix, summing those values across the whole matrix, and then dividing by the total number of trips in the matrix. This gives me the weighted average trip length in the matrix. I've effectively done that using a sum product function in Excel, where I take the sum product of the final trip matrix and the skim matrix, and then divide that result by the sum of the trips in the skim matrix. This then tells me that the average trip length in my matrix at iteration 4 is 8.3, which is a little bit less than the 11.5 that I'm looking for. So what this tells me is that my initial estimate of the deterrence function parameter of -0.2 was incorrect. My initial guess was wrong, and I have to alter that guess and rerun through the whole process. This is what I've done in iteration 2. This time I've changed the deterrence function value to -0.1. The process is then repeated, starting by applying that new deterrence function to the skim matrix, and then running through the same iterative process of applying row and column balancing factors in turn until we get down to the 4th iteration. We get a slightly different version of the matrix. Again, this time the row totals equal the production values and the column totals are much closer to the attraction values. When we calculate the estimated trip length for this matrix, it comes out to a value of 10.0, which is heading in the right direction, but not quite close enough. Finally, on our 3rd iteration, I guess a value for the deterrence function of -0.035. It's the same productions and attractions, the same observed trip length, the same skim matrix. The only thing that I've changed is that alpha parameter that I'm using in the deterrence function. Again, when we apply that deterrence function, that new deterrence function of -0.035 to our skim matrix, and run through the row and column balancing exercise, eventually when we get to iteration number 4, we get a slightly different trip matrix, still with 1000 trips in total, but this time, just after 4 iterations, the sum of the rows and the sum of the columns exactly equal our zonal production and attraction targets. Also, when I calculate the average trip length for this matrix, it comes out to be 11.5, which is exactly the same as our target value. At this point, the gravity model is said to be calibrated, and the deterrence function parameter, in this case -0.035, is then held constant for this trip purpose. For your information, the three different deterrence functions look like this. In iteration number 1, we started with a value of negative 0.2. In iteration 2, we increased it to or decreased it to negative 0.1, and then finally we changed it to negative 0.035. While these curves look similar to one another, if I plot them in if I non-dimensionalize them so that for cost value of 5 they all start with a value of unity, you can see that the deterrence function in our final iteration, the red line, is much flatter or less steep than the deterrence function that we used in our first iteration. This means that we will get more longer distance trips using the red line, and we will get more shorter distance trips using the blue line. And that's exactly the result that we achieved in our 3 iterations. You'll recall that using our first guess of negative 0.2, we got an average trip length of 8.3. Then that value changed to 10.0 for our second guess, and finally in our third guess, when we changed the deterrence function parameter to negative 0.035, we got an average trip length of 11.5, exactly the same as our estimated, exactly the same as our target value of 11.5. Thank you.